Hey class, Adam Ward here. I want to look at the example problem 5.15 out of our Minds textbook together. I like this one because it's a great example that requires us to combine energy balance and mass balance approaches to solve a problem. So here's our setup. We've got a uranium nuclear power plant, and what we're told is about 1/3 of the energy that's actually generated turns into electrical energy, meaning 2/3 of it is lost. And in this case, the predominant loss is with cooling water, so managing heat inside the plant. We've got a flow in a river upstream of 100 cubic meters per second at 18 degrees C. And here's what we're after. How much energy exits the power plant? What's the flow rate if we're allowed to discharge water at no more than 10 degrees warmer than what we take in? And that's a common requirement that you're going to want to minimize environmental impact by controlling how hot that discharge could be. And finally, what's the temperature in the stream after that cooling water gets returned in its heated state? So let's deal with part A first. We've got a power plant. We know that 1,000 megawatts is heading out to the grid. And if this is going to be the case, and that represents 1/3 of the total energy, it stands to reason that the total energy must be 3,000 megawatts, which is then 1,000 going to the grid plus 2,000 megawatts in the cooling water. So 2,000 megawatts must leave in the form of heat energy, as shown here in red. Just as a reminder to you, you can think of the uranium either as an internal source of 3,000 megawatts or an input of 3,000 megawatts, depending on how you want to conceptualize the problem. But it's important to acknowledge that does exist because, of course, we can't create nor destroy energy. We're just talking about changing its forms within a power plant. That's true of every power plant, not just nuclear power. All right, so with this in mind, this idea that we need to get 2,000 megawatts of heat out of the plant, let's think about what that means for cooling water. So here's our power plant again with the energy flows that we just looked at on the previous page. And what I'm going to do is add here some of the information about how the cooling system now works. So we've got a river shown in blue. It's got a 100 cubic meter per second discharge, 18 degrees C, and my rivers are flowing from left to right as always. And what happens in this plant is that cooling water will get pulled out of the river, heated up in the plant, and then discharged back to the river. So I'm trying to show that with the orange arrows that I've drawn on the screen here. And we know from the problem setup, the temperature out could be no more than 10 degrees higher than the temperature in, or in this case, that water going back to the river must be at 28 degrees C. Okay, so the crux of this problem then is really what I'm writing here. For this cooling water, what amount of discharge does it take to move 2,000 megawatts and meet those temperature limits? And this is absolutely an energy balance problem. So the energy in equals the energy out as we're considering the plant. And so the way that I've written this is the energy in, I'm thinking of the mass rate times specific heat times temperature in. So that very first term represents, let's call that term number 1 in orange, and that represents the inflow of heat to the power plant. 2,000 megawatts is going to be leaving the power plant. I'm sort of thinking of that as an input from the uranium. And then on the right hand side, we've got the water flowing out of the power plant. So what flows out must equal what flows in plus the 2,000 megawatt that it absorbs. So that's one key equation for us. A second I wrote above, but I'm just for the good problem solving practice, I'll write it here again. We know how to relate the inflowing and outflowing temperatures. And we're after discharge, which was not yet in this problem. But what we do know about discharge is that our mass rate, and that's a typo, let's fix that. Our mass rate, another way to express mass rate would be a volumetric flow rate multiplied by a density, Q times rho. So with those key concepts, we can make this into a solvable problem. So doing some algebraic manipulation of those three equations, you should be able to end up with the equation that says 2,000 megawatts, the amount you need to add, is equal to the volumetric discharge Q times the density of water rho times the specific heat of water, and then multiplied that by 10 degrees Celsius. Right? The added energy of 2,000 megawatts must be added in such a way that the temperature change could be only 10 degrees C. So if we go ahead and plug in what we know, we can end up with an equation like this. And let me just talk you through. Pause. Slow down, Adam. Let me talk you through this. So in red, what I'm doing is taking that 2,000 megawatts, converting it into watts, so 10 to the 6th watts per 1 megawatt, and then I'm converting it into joules per second, so 1 watt being equal to 1 joule per second. On the right-hand side of the equation, we've still got that unknown discharge, Q. I'm plugging in the density of water, 1,000 kilograms per cubic meter, the specific heat of water, 4.186 joules per kilogram per degree Celsius, and 10 degrees Celsius, which we had before. Now, before I move on too far, I'm just going to take stock of my units because I see lots of things going on here and I want to make sure I get that right. So on the left-hand side, I have units of joules per second. And you can see in this light green color, I'm going through and canceling out watts and megawatts over there. But what about the right-hand side? I can see that my kilograms and my degrees C will cancel very clearly. I didn't have units on discharge, and so what I'm trying to indicate here in the dark green pen is that this discharge has units of cubic meters per second. And so if I have cubic meters per second, those will cancel out with what's in the denominator from density. I end up with joules per second. I draw a happy atom there because my units work. And if I can keep track of my units, odds are I'm going to get to the right answer. So I'm feeling good about this. I've got a solvable equation. And so I can go ahead and solve for a discharge of 47.8 cubic meters per second. So in other words, in order to keep this plant cooled, and not discharge water hotter than 28 degrees C, you're going to need to pump almost 50 cubic meters per second, or half of the river flow, through that plant. All right, part C of this problem asked us, what's the temperature in the river after this happens? So here's our power plant and our river again, and I'm just going to go ahead and label some things that we know. So in orange, what's going on upstream of the power plant? That was given information, 100 cubic meters per second, 18 degrees C. We just figured out the discharges into and out of the power plant, shown in light blue with a temperature of 18 degrees C, the water that comes in, and then leaving the power plant, 28 degrees C. At the downstream end, the point that I've shown here in black, what you can see is a discharge of 100 cubic meters per second again at an unknown temperature. And just for solving the problem here, I'm going to define this point 2 in the middle. So after you pull the water out, but before it gets returned, you'd have 52.2 cubic meters per second of discharge, and that would still be at that 18 degrees C. So what you can do here is draw yourself a control volume and set up an end member mixing problem for the outflows. And so we can mix together our two temperatures, the red and green, to get the outflowing temperature in black. And again, this is end member mixing. This is hopefully comfortable for us at this point in the semester. So plugging in our values, we know our discharge for our cooling water, 47.8 at 28 degrees C, left in the river, 52.2 cubic meters per second at 18 degrees C, 100 cubic meters per second at the downstream end at the unknown temperature T3. And what we find is that the river will have reached a temperature of 22.8 degrees centigrade. And so if you are a resource manager, this is an extremely important calculation to you. you want to understand the impact on the river in a few ways. One, at point number 2, you've got discharge cut in half. What is that going to do to habitat? What is that going to do to velocities? Is that going to cause sediment to deposit where you don't want it? And then downstream of that discharge, you've raised the temperature of this river from 18 to almost 23 degrees Celsius. Is that going to stress some organisms? Is that going to push some fish to a point where they're not able to grow or they're not able to reproduce? And so these are really important calculations as you would be thinking about permitting an operation like this. Finally, just to give you the schematic out of the textbook, this is what Mines calculated. Note that Mines has flow going from right to left. And in this problem, the setup was that it was described as efficiency in the textbook. And just a quick reminder, efficiency, sort of the underlying concept is what fraction of the required input gets turned into what you wanted it to. Right? So in this case, you have 3,000 megawatts of energy sort of input to the plant from the uranium, if you will, and only 1,000 of that turns into electrical energy. So your plant is 1/3 efficient or 33% efficient. I believe that this writing of 1/3% is not true. This, I think, is a typo. You should either say your plant is 33% efficient, or you should say it is 1/3 efficient. What you should not say is that it is 1/3%. 1/3% is 0.00333, and that's not what is set up in the problem. All right, class. So the reason I like this one is this requires us to know something about mass balances. It requires us to know about energy balances. It requires us to do end-member mixing. It requires us to understand the concept of efficiency. And it requires us to get familiarity with units associated with energy and see how mass rates, volumetric flow rates, joules, and watts all come together in these energy problems. So in many ways, an energy balance is identical to a mass balance problem, right? Keeping track of ins and outs, keeping track of our units. But I think this one is really good practice because it pulls that all together. Okay, I hope this helped you all understand energy balances a little bit more, and I will look forward to seeing you all back in class. Thanks, everybody.